once upon a time, in a galaxy not so far away, Ms. G's class was learning all about lesson 7.6, exponential functions. Before we get into exponential functions, we need to do a quick review over linear functions. So remember, a function is something where the x value does not repeat or each input has only one output. The functions we're used to seeing are linear functions, or y equals mx plus b. When we look at a table for a function, we notice that it has the same pattern. Here, 5 to 8, we're adding 3. 8 to 11, we're adding 3. 11 to 14, we're adding 3. So it had that same recurring pattern of addition. And on the graph, if we looked, we saw that it made a line. Now, exponential functions are very similar. However, now we will see we have y equals a times b raised to the x power. So we will have two numbers, and one of them will be raised to some power. For example, let's look at y equals 2x. If we wanted to put that into a table, we do it just like we would have done a linear function where you plug everything in. If we go 2 raised to the negative 2 power, that's the same as 1 over 2 squared, or 1/4. If we do 2 raised to the first power, to the negative 1 power, that would be like 1 over 2 to the 1, or 1/2. 2 to the 0th power, that would be 1. 2 to the first power would be 2. 2 squared would be 4, and I added 3 just for safe measure. 2 to the third would be 8. If we wanted to go through and graph these, we would start at negative 2 and 1/4, negative 1 and 1/2, 0 and 1, 1 and 2, 2 up to 4, and 3 all the way up to 8. So if we connect our lines here, we see that our exponential functions look like this, where they curve up very quickly. When you are asked to graph the equations, you're going to plug them into a table just like you normally would with other functions. 3 times 2 to the negative 2 power, that would be the same as 3 times 1 over 4, or 3/4. 3 times 2 to the negative 1 power, that's the same as 3 to the 1 times 1/2, which would be 3/2. 3 times 2 to the 0, that's the same as 3 times 1, which would be 3. 3 times 2 to the first would be like 3 times 2, which is 6. And 3 times 2 squared would be 3 times 4, or 12. Taking those values that we were giving in the table on the previous slide, negative 2 and 3/4, negative 1 and 3/2, 3/2 is like 1.5, 0 and 3, 1 and 6, 2 and 12 would be all the way up there. You draw in that line, connect those dots, and we see again a curve that increases very quickly. Now that's it for lesson 7.6, so let's move on to 7.7, exponential growth and decay. We're going to be using the same equation as we did in lesson 7.6. We're looking at y equals ab raised to the x power. Remember, just that b is raised to the x power. when we're looking at it in terms of growth and decay, A is what we will plug in for the initial amount, and B is where we plug in our growth or decay factor. If B is greater than 1, then this will be a growth model. If B is less than 1, then it will be a decay model. Growth and decay models have graphs. If it is a growth model, it will look like this, where it is increasing. If it is a decay model, it will look like this, where it is decreasing. Now we're finally getting to the time where you guys are going to be able to use calculators. Woo! Yeah! Woo, 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 woo. So, get your calculator out and let's get started. The population of fish in the lake decreases by 6% annually from 2,000 fish. So our equation is y equals ABX, where A is our initial amount and B is our growth or decay factor. So let's plug in our information. For A, our initial amount, we are going to put 2,000 because it says it's originally 2,000 fish. Times B, it says it decreases by 6% annually. So instead of 100%, it's going to go down. So the next year, it will only be 94%. So I'm going to say times 0.94, that's 94% written as a decimal, raised to the x power, where x is the amount of time. We want 3 years, so instead of x, I will say 2,000 times 0.94 cubed. Plugging that into our calculator, 0.94 raised to the 3rd power times 2,000. That means in 3 years, we will have 1,661 fish. Now, if you plugged that into your calculators, you would have gotten 1,661.168. Now, I'm not going to count 0.168 of a fish as a fish, so I'll go ahead and call it 1,661 fish. Sorry, 1,661 fish. Here's another one. The amount of money spent at a restaurant has increased 7% each year since 2005, when $300 billion was spent. If the trend continues, how much will be spent in restaurants this year, 2015? So again, our equation is y equals AB to the x. A is the initial amount, B is our growth factor. So y equals initial amount is 300 billion. Our growth factor is 7%. So now we have 7 more percent than normal. Notice here, I didn't just say 7%, I said 107% because we are increasing each time. Plugging in we're going 10 years, so it'll be 300 times 1.07 to the 10th power, 1.07 to the 10th power times 300. That means in 2050, if the trend continues, there will be about $590 billion spent on people going out to eat at restaurants. Now the final thing we need to learn, someone may want to make a poster about it, is compound interest. This is when a bank will give you interest not just on the amount of money that you put in, but on the interest as well. So the equation is A equals P times 1 plus Rn raised to the nt power. Now here's what everything means. A is the balance, the initial amount, is the total balance at the end of the interest stuff. P is the principal amount, or what you decided to deposit in the beginning. R is the interest rate, and it needs to be written as a decimal. N, which you will plug in twice, is going to be the number of times the interest is compounded. So it may be compounded once a year, or twice a year, or 3 times a year. It'll tell you in the problem. And T is the time in years, so 3 years, 4 years, 5 years, etc., etc. So let's go ahead and solve a problem. $20,000 deposit earning 3.5% compounded monthly after 10 years. So our equation is A, or the total final balance, equals P, the principal amount, times 1 plus our interest rate divided by the number of times compounded, raised to the number of times compounded times the number of months, or the number of years, sorry. Let's plug everything in. P, our principal amount, is $2,000 or $20,000 times 1 plus our interest rate written as a decimal. Remember, to turn percents to decimal, we move our decimal place twice. 0.035 over N is the number of times it's compounded. It's compounded monthly, so that'll be 12 times total in a year, raised to the 12 times 10, whereas 10 is the number of years. If we plugged all of that in, our final answer would be $28,366.90. I hope that this video was helpful. In honor of Star Wars, our joke today: what do you get when you cross an elephant with Darth Vader? An elevator.